How are you with the story of Rooflogic? Where am I here? Give me one moment. Will I start that?
Start at the top.
Oh, we are. Why are we on that? We should be on the front. Oh, look at me, starting from the beginning. Rightio, Sylvan, are we good there? Is it good on screen?
Yes, all good.
Awesome.
Thank you very much. Takes away, Graham.
Thank you, Victoria. Nice to be here. And yeah, thanks for everyone who's joined us today. And there may be some others as we go through the 20 minutes or so we can have a chat together. And obviously feel free to make a note of those questions as you go along and add them to the chat. I'm very happy to have a conversation at the end as well. So just briefly, I guess, a little bit of information around Rooflogic, why it existed, a little bit of how it came about, the thinking behind it, and what we've been involved with in terms of system development, system testing, and projects over the last decade or so since we've been since Rooflogic has existed, a relatively young company, and some sort of understanding of how we happen to be part of the roofing landscape in New Zealand is probably helpful. But if I go to the first slide, I was a roofing contractor for a long time, I guess about 25 years, and what I began to notice more and more as we were installing commercial roof systems, what sort of now have been, I guess, become referred to as cold roofs, but they were just called roofs 20 years or so ago. And these are some examples of cold roof assemblies. And what we were noticing as installers is we were getting increasing number of kind of inquiries, post-install, questions about the performance of the roof systems that we were installing. They were designed that way, they were drawn that way, they were consented that way, and we installed them as per the detail. But we would go back to our projects after we completed them, and we'd see some of the sorts of things that I'm showing in these slides here. The one on the bottom left of your screen is it's a school project. We were called back 12 months after the install because the school was concerned about the amount of mold and condensation that was forming in the roof cavity and wanted to know if there was something wrong with the install. There wasn't much wrong with the install, but there was actually something fundamentally wrong with the system design, and the system failed to manage vapor drive, and we were getting within the sealing cavity a huge buildup of condensate, liquid condensate, high levels of humidity, resulting in liquid condensate, but also corrosion of metallic surfaces, and also, as you can see, examples of mold forming so on layers of the roofing system and adjacent building components as well. So this took us on a bit of a journey to understand why this was happening, and try to understand how, as installers, perhaps we could do things differently or more effectively and avoid some of the issues that we were starting to see more and more as buildings effectively became more tightly constructed, so much more airtight, particularly in terms of the walls, window to wall junctions, those sorts of things, with the roof still being a relatively poor cousin relative to the walls, and becoming increasingly an issue in terms of seeing these issues with condensate, mold, and corrosion. So we spent some time overseas. We spent some time talking to and engaging with some of the best known building scientists, building physicists around the world, visiting them, having them visit us, and really digging into sort of some of the fundamental flaws in the way that we were constructing roofs and the implications of that. And through that process, I stopped, I guess, my contracting career, if you like, and realised that if we were going to affect some positive change in the industry and design buildings, and particularly roofs that were warmer, drier, more thermally efficient, more acoustically efficient, and didn't have the sorts of problems that you see on your screen now, then that would require us to kind of leave the the enjoyable game of being a roofing contractor behind and start a company where we could provide some real solutions more broadly across the industry. And these solutions have now, more recently become known in New Zealand as warm roof assemblies. And it's a slightly kind of misleading term, but we can use it today as a way of kind of comparing what Rooflogic offer compared to maybe some of the more traditional roof assemblies. And these are some of the assemblies that you see in front of you now. These are a range of our metal roofing assemblies. You'll see that there's a range of different insulation options available. It can be stone wall. We've got PIR board. We've got low lofted glass wall insulation in one of the systems, bottom right, that sits within a structural cavity that's formed with our structural post and rail system. You can see there's some green boards in there as well. That are acoustic layers where we add mass into our system so that we can achieve higher rates of performance in terms of rain noise or sound transmission, attenuation, and those sorts of things. And what you'll also notice with all of these systems is there's a little silver layer that sits on top of our what we call our liner deck or our base deck, and that's the location showing where our vapor control layer sits within the system. On the system on the bottom right, the liner deck in this case is detailed quite comprehensively with some complex infills and some seals to function as our vapor control layer. So there's not a separable vapor controller in the system, but it is designed with a liner deck that has vapor control. Then we go to our membrane roof systems, and you'll see that although the icing on the cake is different in terms of either a single ply or a two-layer modified bitumen membrane being installed, the key component there that remains is that vapor control layer that sits on top of the substrate, whether that substrate is a structural base deck, whether that substrate is plywood, or whether that substrate is concrete. And if I go to this slide, and if we just focus on that top render, you can see, if you look carefully, it should be a more heavily dotted line, I think. But if you can see, if you look carefully on that top render, you can see above the line deck, you can see that vapor control layer dotted in. And what this high performance, highly vapor resistant control layer is doing is separating the internal and the external environment. So with those systems that I showed right at the beginning, those photographs I showed right at the beginning, where we could see that condensate, where we could see that mold, we could see that corrosion, what was happening there was that internal environment was moving through the ceiling assembly, through the internal insulation layers, cooling as it did so, increasing therefore in relative humidity, and basically hitting those metallic surfaces which were below the dew point of the air as it moved through, because the air was becoming cooler and increasing in relative humidity, and it would hit those metallic structures and it would condensate, and it would create mold, and it would create corrosion. So what we're doing with these systems, in really simple terms, and there's many layers to the physics, but this is kind of at its most simple, is what we are doing is we're forming a separation layer between the internal and the external environment. When we can separate those environments, we can then control the internal environment in terms of air quality, and eliminate that condensation risk that is associated with systems that have or don't incorporate vapor control. And we can see that the insulation in all of our systems for New Zealand sits above the vapor control layer. So we have a vapor control layer and then a continuous layer of insulation that sits beyond the vapor control layer that maintains all of those internal surfaces, the liner deck, the base deck, other substrates, purlins, whatever it might be, retains them at a temperature which will always sit above the dew point temperature, so you eliminate that internal condensation risk or interstitial condensation risk within layers of the roof assembly. So that's the basic kind of principle behind our systems, and obviously there are multiple layers to that. Where is the building? What is the building used for? What is the what are the number of people that are using the building? Where is it in New Zealand? All these sorts of things has to be factored into the individual project by project analysis we do to demonstrate that the system applied to a specific building. Is it a warehouse? Is it a school? Is it a brewery or a commercial laundry? That are appropriately designed to manage any condensation risk in terms of the assembly, but also in terms of the building and where that building is. And what we find when we pull our roofs apart is that the science is backed up by real life performance. So these are some roofs that we have disassembled, several years after they were installed, often in very cold conditions, often in buildings that have a very high internal vapor drive because of the use of the building or the number of occupants or whatever it might be. And we see that the effect of continuous insulation sitting above a high performance vapor controller means that there is no condensation forming potential interstitially within the roof system. And you can see that on the right with our what we call our fiber therm system, where that low lofted insulation is sitting within a structural cavity, that the product is still beautifully lofted. There's no sign of condensation. You look at both of those photos. The one on the left is the top deck is sitting on top of a continuous layer of PIR board, Kingspan PIR board, and you can see there that how clean the underside of the metal roofing is, and really no suggestion that there has ever been any condensation forming interstitially within layers of the roof system. And here are just a few examples of some projects we do with the different types of systems that we use. We do a lot of school projects, and there are 3 school projects shown there. Shirley Boys, Avonside Girls, the one on the bottom left in Christchurch, the largest single school campus that's been built in New Zealand, about close to 20,000 square meters of warm roofing. So that's the top one, the fiber ultra-therm MSR system, and the other schools are similar sorts of systems. That the bottom render you'll see we're showing a slightly different insulation. We're using a high density stone wool product that was used on the Christchurch Convention Centre project, which you see top left in this picture, and that was really driven by the requirement for high levels of acoustic performance. Stone wool particularly performs extremely well in terms of acoustic attenuation, particularly when it's coupled with one or multiple layers of a high mass acoustic board as well. They're just examples of kind of how the systems are installed, depending on the thickness of the insulation, depending on the type of top skin that's used, is it a trapezoidal or a standing seam, whatever it is, then there'll be different designs in terms of how things will work structurally, in terms of load path, back to structure, and those sorts of things. But fundamentally, again, with these systems, you can see there's a substrate, in this case a liner deck, there's continuous vapor control, and then sitting above that there are continuous thermal and acoustic layers that provide that thermal performance, that management of condensation risk, and those high levels of acoustic performance. There's just a little bit of a drill down into the project at Christchurch, the convention centre, and something that's kind of interesting here. If you look at the bottom kind of line of photographs and you go to the far left, that's our perforated liner deck or liner tray in this case, which we use on facilities, usually public facilities, where they are looking to achieve internal sound absorption without the introduction of additional acoustic treatments or suspended ceilings internally. So you can see the perforated liner deck is installed. Then the next photograph is our acoustic baffle that's installed. The next photograph is looking up at the underside of that liner tray with the acoustic baffle installed. So in that situation, we were able to achieve a really high, what we call NRC performance, noise reduction coefficient, of between 0.95 and 1, which is pretty massive in terms of internal sound absorption, so that we could achieve those NRC requirements for this project without having to introduce any additional internal acoustic treatment for noise absorption. And then the other photos, you see the multiple layers of stone wool that have been used there. Not so much because that level of thermal performance was required, but because the sound transmission management was really important, being a convention centre facility as well. So it's just kind of drilling down into one of those specific examples. Here's some examples of our fiber therm system installed. pretty exciting now. We have a product in the market called the Fibertherm X system, which is fully kind of locally designed structural post and rail system. It's aluminium componentry, phenomenal durability, and designed with increased load performance in terms of point load resistance, distributed load resistance, uplift resistance for wind load management, those sorts of things. So pretty exciting. That's being used on a number of major projects around New Zealand now, and just its ability to manage everything from the seismic forces and the wind forces that are often quite unique in terms of their specific intensity in New Zealand is something that this new system is really well placed to manage. And you can see that this system works really efficiently, really cost effectively when we're looking at installing a true warm roof system in some of these more large format commercial industrial applications. You'll see bottom right is an interesting one. That's actually showing an office building that's used the Fibertherm system, but you'll see in that photograph we actually have our perforated trapezoidal liner. So it doesn't quite have the same NRC performance as our liner tray. It's about 0.7, 0.75, but still more than adequate to manage noise absorption within an office space. So that's often used and incorporated within our Fibertherm systems as well. And then we move on to our membrane systems, obviously well suited to more complex detailing, more complex geometries, and just a few examples there of some projects that have been done with these two different membrane options. One is our Fibertherm, one is our Fibertite, which is a high performance single ply, and the other is our Durbigum, which is a modified 2-layer bitumen. Pretty amazing product in terms of the quality and performance. And just a couple of examples there of the products being used. And it's not so much specifically about the products, but I guess this is just talking about how we can install warm roof systems. This was done on a component basis with individual kind of roof sections being craned into site, and then the final detailing being done on the roof, but most of it being done off-site as part of the fabrication of the roof system. So yeah, just being installed there and then kind of linked together with ridge and valley detailing to provide the sort of the geometry that you see in front of you in terms of that roof system. The Fibertite's quite nice in terms of the complex detailing that it allows when we have some quite complex structural elements that have to be accommodated within the kind of waterproofing envelope. Recently completed project is another convention centre in Christchurch where STC performance important, our large scale warm roof with membrane installation. Probably my favourite job is this is a Durbigum job, and it's a beautiful warm roof assembly that was installed on the St Andrews College Chapel. So thermal performance, vapor control, acoustic control, and obviously just a high performance membrane to provide long-term weather tightness. And the look of Durbigum is really well demonstrated here, and just in terms of the quality and retention of the mineral slate and those sorts of things, which are quite unique to the Durbigum membrane. We often talk about systems and not products, and I think we all can kind of relate to this. But on a project by project basis, one of our focuses is to make sure that we do detailed hygrothermal and thermal analysis on the systems that we provide, make sure they meet the requirements of the project. Structural designs are obviously specific to a project because every building shape and size and location is always going to be subtly different or significantly different, and so about providing good guidance for installers around the appropriate way to install a particular system on a particular project is some of the kind of the guidance and the information and the support that we would provide. And we've got to add to that acoustic performance as well. And just an example of some of the testing we do on site, off site, increasingly fire performance is being evaluated along with acoustic performance and those sorts of things. But just an example of kind of the testing that we do. And I just wanted to finish up that. We're doing really well with 25. Just finish up by I guess showing a video. and I'll talk over it as it goes through. But this is just an example of a large format retail facility that was installed a few years ago down in Christchurch, where we used our fibertherm system. So the liner deck is installed first, and then once the liner deck is installed, the structural post and rail is assembled. Installers really love the system. The line deck goes down, the building's enclosed, the roof is off the critical path in terms of the construction program. You know, in less clement weather, posts and rails can still be installed, you know, safely from above and below. And then when we get that right spell of weather, we can get the insulation and that metal top skin installed. So you can see here the insulation is being rolled out, trimmed under the structural rail, and then the metal top skin being installed. These are probably 25, somewhere between 25 and 30 meter sheets, I guess, which obviously for commercial roofs is pretty standard. Close-in is very quick. This is a 5,000 odd square meter roof. You know, installed to close in was, I think, 5 days, and then another 10 days and the roof was complete. So certainly has some advantages from an installer point of view, and obviously from a long-term performance, thermal performance point of view. Great to have a warm, high performance, cost-effective warm roof on some of these large projects as well. So yeah, that's a bit of a rundown. Sort of started with the why we do what we do, and I guess just want to finish with the thought that what is Rooflogic and what isn't it? Well, we're not we're a warm roof, as I say. That term is probably slightly generic, but we're a warm roof systems supplier, and that's all we do is warm roofs. That's our focus, that's our passion. That's what we think adds some real value to the buildings that people live in and work in and learn in. So that's where we think we can really add some value to the built environment in New Zealand, is by offering those systems. If you want a standard roof or a cold roof system, or you want some membrane on ply, or a metal roof that isn't a warm roof, then there are plenty of other people that can do a very good job of looking after you. We're a one-trick pony in terms of offering warm roof solutions. And sometimes, I know it sounds grandiose, but sometimes I say we're a little bit like Tesla, as opposed to Ford or GM. If you go to Ford or GM and you want an electric car, but it sounds like it might be a bit expensive, or you're not quite sure if you're ready for the leap, then they can always offer you an internal combustion engine. And it's the same if you can offer warm roofs, but if it doesn't quite work for your budget or whatever it might be, you can offer a cold roof as well. We're more like Tesla. If it's either an electric car or it's nothing at all. And with Rooflogic, it's either a warm roof or it's nothing at all. So that's our niche. That's where we kind of play, and that's where we think we can add some value in terms of, say, the built environment and the way people can kind of connect with their buildings in a way that's sustainable and comfortable and enduring. So that's us in a nutshell. And yeah, if there are any questions that have come up as we've had conversation, or some questions that we want now, then that would be appreciated.
Just looking at the side there, was NRC noise reduction coefficient?
That's correct. Yeah, I'm not a. We have someone who's very kind of well recognised in the kind of the acoustics sector, who works for Rooflogic, and she could explain acoustics till we're blue in the face. But that is correct. That it means noise reduction coefficient, and that's in very, very simple terms is about managing reverberation time and providing a system that internally absorbs that noise that is created within the building space. Yep.
How can expired coils be used for their liner deck?
Potentially, yes. I guess it depends why they're expired and what's wrong with them, or if they're defective in any way. But obviously, the line deck is internal. The line deck sits within a dry space. As I say, you've got your vapor control and your insulation layer sitting above the liner deck. So really that's about evaluating what expired means, if there's anything wrong with the coil, and if that would impact durability relative to the internal exposure that the liner is going to be exposed to. But more than likely the answer would probably be yes. It would probably be a good place to use them.
The next question is, the position of the green acoustic board differs from rock wool to PIR. So perhaps if we just talk through the acoustic board and just its placement.
Yep. So I know the render that you're referring to. That render is actually not only did it change from PIR to stone wool in that render, but also the top skin changed from a trapezoidal top skin to a standing seam. Now the reason that if we do have a acoustic board, and we don't have to, but if we do have an acoustic board within a system that has stone wool insulation, then we will place that, and then we have a standing seam, we will place that acoustic board on top of the rock wool, because the clip for a standing seam profile is relatively small in terms of surface area. So the ability to bear the clip without depressing into the buildup, the insulated buildup, is better for a clip of it sitting on top of an acoustic board, because it's much higher density than stone wool, when we have a standing seam. If we are doing standing